Hello YouTubers, Troz here, and today I thought I'd do something a little different in this video. I've set up a few displays and things in the past, and I recently showed a video with a text display, but today I want to show how I designed that and how you can make relatively space-efficient displays. This is pretty large. But for what it's actually doing, it's pretty space efficient. You can see we're displaying text up here of a particular item, and then in the big numbers we're displaying how many of that item we have. If we don't have any, we're cycling fast through the items, but we come to an item we do have, we hold on that item for about 5 seconds, and then we switch on to the next. And besides just items, this has a few other things that will display that are hooked up to it, like the power level and rockets launched, and that will actually work. I have a little circuit over here. How many times Exterminator got ran over by a train, or how long you've been playing in seconds, and actually counting up. There's the power, and now we'll cycle around. Yeah, I actually sort of designed this for the Factorio server, even though I'm not a part of that. Yeah, so here we're at 15 coal, and you can see I have this box over here in logistics, and that's what it's displaying. These are not all the items in this logistics network, but it's some of them. So you can see iron plates. I obviously have 100 somewhere else. Copper plates. Alright, so let's actually get on to... This is a very complex thing. I'm going to start out simple. And about the simplest display you can make is something called a 7-segment display. And it's the kind of display calculators use, or some like alarm clocks, desk alarm clocks. And let's put down some power. I am playing right now in creative mode, which is a mod that basically you can build whatever you want. All these have infinite buttons. You just click it, you get what you want. They add some things like energy sources that will provide as much power as you need for whatever you're looking to do. So, yeah, that's going to make the demo a lot easier. So I am making a basic 7-segment display. Each one of these 3 groups of light lamps are a segment. Thank you, autosave. And there, it looks like an 8, but you can light up different segments to make different numbers. For example, if we light this one and this one, it looks like the number 1. You know, if we light this one, this one, this one, this one, this one, it looks like the number 5. So, how do you hook this up so that it does that for some value? Well, let's first, well, maybe not first, but we'll put a chest down here, and we'll pipes. Great. We'll put a 5 pipes in it. We'll do 4 actually. But we want this, not just to work for 4, we want to work for how many pipes are in this chest. Well, so the first thing we want to do is wire up all these segments, and I'm just clicking on each one in turn. You can connect them all in a loop like that. I'm hitting Q to disconnect. You can put it back in your inventory to also disconnect, like so, but Q is much easier, I find. And yeah, it doesn't matter if you use red or green wire. They both act the same, except red wire signals won't mix with green wire signals unless you use a combinator of some sort to do that. And we're gonna set these up so each segment can be turned on and off individually. Now, if you go to the Wikipedia article about 7-segment displays, you see that traditionally each of the segments are labeled. This is A, B, C, D, E, F, and G. So we will do that. So we'll go over here. We'll use these virtual signals. We'll call this A if that's greater than 0. I'm just going to click Use Colors. We're not really going to use that. I'm now Shift right-clicking to copy, Shift left-click to paste. And at first, I'm going to paste this seemingly randomly, but basically I put one segment in each group. I'm going to change now that A to a B because this is segment B. Copy, paste, paste. Your C. Copy, paste, paste. Your D. Copy, paste, paste. It was U I did. Your E. Copy, paste, paste. Did the top one. F. Copy, paste, paste. And I believe I did U. U, R, G. Copy, paste, paste. So these wires can carry signals, and by hooking them up to a pole and hovering over the pole, it will show what signals it has. Right now, it has no signals. But let's put down a constant combinator, which will output whatever signals you want. So if I want this to display the number 1, I just need to output A, not A, but B and C. B and C. And look, it's displaying a 1. Great, but we don't want it to display 1, we want to display the quantity that's in this chest. You know. Let's do what's it? Well, for example, I should have left B and C. We'll do the 4 that we're trying to get, which would then be A, B, C, D, E. We need F and G as well. F and G. And look, there's 4. Great. It's not what we want, though. It sort of is what we want, though, just not right now. So let's hook this up. It doesn't actually matter where. Let's get it to display a 0. So that would be A, B, C, D, E, and F. That's 0. Great. Disconnect there, in fact. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 0, 1, 2, 3, 4, 5, 6, 7. 9. Yeah, okay. Yeah, it's 1 more than the height, it turns out. So now let's get 1. So basically we're programming each of these for each number. 1 is B and C. Great, turn that off. 2 is A, B, not C. We want D, E, and G. There's the 2. 3 is A, B, C, D, and G. 4, not A, B, C. It actually doesn't matter what order. G and F. You know. Yeah. 5 is A, not B, but not C. Yeah, C. D, not E, but F and G. To disconnect the wires, which I didn't specify before, you just make the connection again, and it will disconnect. Let's connect you up. You're 6, so you should be A, not B, but basically all the rest. G. Great. 7 is relatively simple. It's A, B, and C. Eight, also relatively simple. It's all of them. E, F, and G. And then finally, 9 is A, B, C, not D or E, but F and G. Great, but how do we decide which one of these to hook up? Well, that's where the decider combinators come in. We will put a decider all along each of these. And we'll put this down as our test. So, we want to have one of these set for each digit, and then we'll connect all of them together. So only one of them will be outputting at a time, but whichever one outputs will send the signals for that appropriate number. For example, if this will be our input for now. And we need to hook with a different wire so we don't cross these. Hook this to here, and then I'm hitting Q. So each one is only hooked across. You know, if we use the red wire, well, then all their signals would mix. We don't want that. That's why I'm using green. So we're going to set this, let's call it output N. We're going to set it to 0. And then we want to say here, if N is 0, whatever the input is, we want to output everything. So N is 0, and so these signals, A, B, C, D, E, F, are being passed along. A, B, C, D, E, F. Theoretically, N should be output as well, but N is 0. So let's change N to 1. And yeah, 0 signals don't display. Now we're not getting anything. Well, we haven't set 1 up. So let's copy this. I'm going to shift right click, paste it. But this is not right, but it sets all the settings except we want this now to be N equal to 1. So when N is 1, we are outputting B and C, and it also happens to output N, but we're not concerned with that. So we're going to do the same here. This should be 2. Thanks. You're 3. I wish it would let me type right into here. Because this is a 2-step process, takes a little longer. 5, 4, 5, 6. You're 7. 8 and 9. And we're basically done now. So if I come over here, let's drag this out of the way, and I drag this from 1 to 2 to 3 to 4, 5, 6, 7, 8, 9. That works. Now if I go higher, it doesn't. It's only 1 digit. Now the only thing we need to do is to change pipes to N if we want to do this. So I'm gonna hook the output to there, those inputs, exactly where we had the constant combinator hooked up. I'm gonna hook this chest to here, and I am going to say take pipes are over here, add nothing, but output it as n. And as you can see, we instantly got a 4. If I open the chest, and actually I can drag this down a little, and I take out half, it goes down. As I put one in, it goes up. We've got a 7-segment display. And it's decently sized. I won't say it's the smallest, but it's decently sized. Speaking of smallest, you can actually make a smaller display, you know, with only 2 lights per segment if you want. 1 light per segment, it's possible. It doesn't really look right. You know, that wouldn't, even lit up, it wouldn't really look like the numbers. But this works. I could just hook this up, hook here. Notice nothing happens. We just now need to copy. That's like an A. This is a B. S, C, D, E, F, and G. And now, yeah, drag this down. 0, 1, 2, 3. Oh, 3. 4. Great. That works. We need multiple digits though. What if we had 10 or 50 or 100? Not 100. I'll put 54. Well, this is not showing anything. How do we deal with that? Let's get rid of that. I actually need to move that down a little, but I'll get a blueprint out here. We'll copy. I'll stick this down. That was quite loud. Get rid of those. I'll just move this a little bit. Hook that there. Hook that there. That's how it was. Well, you should have called this D for digit. That's okay. We'll work things out. Now we have a 2-digit number, and we need to separate the digits. So we place, we need to send the 10 digits in on a red line here, and the 1's digit on a red line here. I'll do the 10's digit because that's easier, and then I'll do the 1's digit after that. Just be basically the 10's digit and every digit above it. Yeah, let's go for it. We'll do 3 digits because that will make the example easier. Actually, where did you? Too many blueprints. Alright, there we go. Hundreds, tens, ones. How do we pull out a digit? Again, I'll do the tens digit first because it will explain everything I need. But basically, we just need 2 arithmetic. You're going to be input. To make everything easier, we're going to have one convert it to a letter, and then we'll work on that letter. So pipes convert it by just adding 0 to A, which we'll call the amount. And then each of these will calculate a digit, which we'll call n for number, because I already have these set up for n. So we want to take here and input it here, and input it here, and input it here. And just for showing, this is the 154, which is the 154 pipes that we have. So how do we get out the 10? Well, let's get the 5 into the ones digit. So that's relatively easy. We take A, we divide by, well, we want the 10's position, so let's divide by 10. And output that, we'll call it D here for digit. So you can see D is now 15, but we don't want 15, we want 5. So we'll take that, input it here. We'll take D, and we'll use this. It looks like a percent. It's the modulo operator, technically. If you've done any programming, you may recognize this. But this basically means give me the remainder after dividing. So we want to divide by 10 again. So we have 15 divided by 10 will be 1, but it will give us a remainder 5, and that's what we want. So we'll output that on n. So you see that is 5, and we can hook that right up to here. We have the 5. Great. So for the hundreds, we can do the same thing, basically. I'm going to actually copy this one, paste it here and here. I'm now going to copy this one, paste it here and here. And if I wire everything up, what will we have? Well, we have a bunch of 5s, and that's not right. But here we want the hundreds digit, right? We want the 1. So let's divide by 100. Hey, look, it's a 1. Here we want the ones digit. So let's divide by 1. 154. That's exactly what we wanted. Okay, let's take some out. Let's take 100 out. Well, now we have 0.54. Let's take all but 4 out. Now we have 0.04. That doesn't look nice. So we can do something about that as well. We'll stick in a decider combinator. And there's actually a reason why, well, I have the outputs on these two differently. So we got output of D here and then N here. I'm going to disconnect this one just by running the wire over it. I'm going to actually connect both of these outputs to here, this decider, and then take the decider and go to here. And in fact, it's not necessary for me. If it's 0, I want to display 0, so it's actually not necessary on the ones digit, but on the 10s and above, you want to do this. Keep hitting Q when I don't want. So I want to connect these two together and here. So as we see, D is what we get back when we divide, and then N is the remainder after dividing by 10 again. So if we divide and we find that there's nothing, like D is 0, then we don't want to, this result is going to be a 0, and we don't want that. If we divide and find it's going to be, if we have 105 or 104 in here, and we divide by 10, this is going to come out 10. So D is going to be 10, but no, A, yeah, D is going to be 10, but N is going to be 0. But because D is greater than 0, that means, hey, we need to display a 0 because there's going to be another digit. Either there's going to be a digit here, or there's going to be a digit over here, and we're 0. So we want to say if D is greater than 0, and this is outputting N, then we want to output N if D is greater than 0. Actually, yeah, we want had that in a little bit of a wrong place. We want to hook both of those over to here. Actually, I'm doing this a little bit on the fly. We want to disconnect here and here, but put this up here. Let's disconnect that. So these are still going across. This is going green to here. We're gonna go green from there to here, and we're gonna say that. Let's do it over here. Green to here. Disconnect these. Green to there. Then red. So we're gonna say if D is greater than 0, we're just going to output what we get. And we'll do the same thing here. Actually, I can just copy, paste. Okay, how did I... We got D in 2 places. You have to be... We'll call it P for place. That was... Yeah. And you have to be place. 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 Place is because we have a segment called D. We're already using it for something. So place is greater than 0. Four. And your P. There's 4. Copy, paste, paste. So 4, we're showing 4, no leading zeros. If I put in a few more, 6, let's move this down, 7, 8, 9, 10. And if I put in the whole thing, 104. And there's your 154. So there. I kind of messed it up. I'm sorry. I should have pre-planned a little bit better. So there's a 7-segment display, no leading zeros. However, it's still too big. We have 10 different deciders. 10 different deciders and 10 constant combinators for every place. Well, what can we do? Well, we can get rid of these and these, because they're the same. So we can just take this and go here and here, and then here and here, and here and here, 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 and here and here. There's the 4, and this will let the 5 light up. And this is workable. You know, it works. It's still pretty big. I mean, we've saved some constant combinators, but we still have 10 deciders, or 11 deciders, if you want the no leading 0 per place, and a few arithmetic. Is there a way, you know, of compacting these signals? It turns out there is. There's a few ways probably to do it. To run everything off a single constant combinator. I'm going to show a way ooh, that was loud, sorry. Learn/figured out. I actually saw this technique first in a blueprint that originally was done by Dave MCW. But these numbers in a constant combinator are handled by the game logic. And the game is a 32, well, this part of the game is a 32-bit program. And they're handled like modern computers would handle 32-bit numbers. They're binary, which, if you don't know what that means, is internally it's handled as a signal of 32 on or off, true or false. And the arithmetic combinators have, like, these are, you know, multiply, divide, add, subtract. This is divide but keep the remainder. This is power. But the rest of these deal with bits, or on-off signals. We have AND, which combines the two numbers, and if their bits are both on in the same place, the result, it's also on, and otherwise it's off. Or if it's on in one, or on in the other, or on in both, then it stays on. And XOR, if it's on in one but not the other, it will stay on, otherwise it's off. And then we have some shift operations, which will shift all the bits to the left and add a 0 at the beginning, and you lose whatever at the top. And this will shift them all to the right. You'll lose whatever's at the bottom, and a 0 will be added to the top. And at least in the way I do this, this one becomes very useful. So I wrote myself a little program that, you know, a short little program to take the on-off states for each segment for different numbers. So, like, you know, A is on for 0, and it's off for 1, and it's on for 2 and 3, but it's off for 4, etc., 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 and encode that into a single number that we'll call A. And for me, that number is 3085631488. B works out to be 4, 1, Alright, I'm going to interrupt myself there. This is me a little afterwards of making this recording. I don't really think I explained how I got to these crazy numbers very clearly, so I will do that now. There's really two ways we could do these numbers, basically encoding the shapes of all the different numbers that we want to output onto a single signal. This is the program I wrote to do it, although not exactly, but I'll get to that in a minute. But yeah, what I'm actually encoding is not just 10 different values, but 16. Each digit can actually display a hexadecimal digit, which if you don't know what that is, you don't have to worry about it, except that we can display 0 through 9, and then 6 additional values, A, B, C, D, E, and F. B and D are specifically lowercase because an uppercase B would look like an 8 on the 7-segment display, and an uppercase D would look like a 0. So by doing them lowercase, you can actually make that shape out of the 7-segment display and will be distinct. Specifically, you know, they're different than any other symbol that we're currently using. The closest thing is B, kind of looks like a 6, but the 6 has the hat on top. So it is different. Anyway, we want to encode all the possible shape, instead of having 10 different combinators, constant combinators, with the different values that, whether A should be on for 0, and then, or off for 1, and then on for 2, etc., etc., we want to put that all into one number. The numbers in the Factorio signals are 32-bit ints, so we can, encode this true, false, which is really on, off, on, as ones and zeros. Binary numbers start, at the bottom, so this is 0. It's really the ones place, but this is the on, off, off, on that we see across here. I just do a little math to basically make this bit pattern, and that bit pattern happens to correspond to this number. Now to show how you then decode it, I will pull up this little larger view. Hopefully this is clear, and we'll get a few extra windows here that I'll just use for framing, hopefully, and it'll look good. So what we can do, if we want to display the the character 0, is we can take all of these. With the combinators, there is a everything signal. You can apply a single math operation to all the signals at once. So we can put all these numbers into a single constant combinator, and then apply the same math to all of them. So we can use an AND operation. So if we wanted like these, which will pull out a single bit out of each of these. So if we want to see what's on for 0, we can AND it with the number 1, and we'll get something like A is on, and B is on, and etc., and G is off. Great, that's good for 0. How do we get 1? Because the digits for 1 are represented here. So what we can do is use a right shift. If we right shift by the amount of the digit we want to display, well, if we want to display 0, we right shift by 0, which does nothing, and then we can AND it, and we wind up with that. If we want 1, we can right shift by 1, which is the same, almost exactly the same as, hey, cover this up. Now these are the lowest bits, so when we AND it with 1, it comes out looking like that. So for the digit 1, we want to turn on B and C, but all the rest are off. If we want 2, well, we shift 1, 2. These are the lowest digits now. We AND it, and we wind up with A is 1, B is 1, C is 0, etc., 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 and that works. That's totally way to do it. The thing is that needs 2 arithmetic combinators to accomplish. Can we do it better? Is there a way to do it with only 1? It turns out that there is. Instead of basically putting all the numbers at the, starting 0 at the bottom, then 1, then 2, then 3, then 4, and ANDing after the shift to get our number, if we use a left shift and put all the numbers at the top, we basically get the AND for free. Well, how do we do that? How does that work? So here, the first row is for 0, this is for 1, 2, 3, etc., etc., etc. And the signals in Factorio are 32-bit ints, and they're signed ints, which practically all modern computers use what's known as 2's complement notation for representing negative numbers. You don't need to know what that is exactly, but basically the negative numbers come after the positive numbers. So the positive numbers are any number that start with a 0, like this one, and the negative numbers are any number that starts with a 1. The thing is, it's not just a sign bit. If I made this a 0, it wouldn't be the positive version of this number. There is basically, you have to add 1 to this and then flip all the digits, and that's what the positive version would be. But that's not really what we care about. We just need to know, we can shift this by 0 and look if they're negative. If we want the number 0, we do a shift of 0, and then we look at which ones are negative, and that's the ones we want to light up. So let's do this in the bigger one, which I do have it here. So we shift by 0, and we look what numbers are negative, and basically that's just looking at this top column. That's kind of like the AND was pulling out a single column. And so yeah, that's the same result. Now if we want 1, we shift left by 1, and when you shift left, all the digits at the top pop off and disappear, and so it's as if the number becomes this, just with an extra 0 here. And now we look at which ones are negative, and it's those two. So by looking at what's negative, it's like we're getting the AND done for free for us. We don't need to hide. We don't care which negative number it is, so we don't care what these digits are. We just need to look if the first one is 0. The first highest place is a 0 or a 1. With the other way, if we're looking if it's positive, well, we can't have these in the way because we don't care about those. We only care about the lowest one, and that's why we needed the AND. But by looking for a negative, we're getting an AND for free, basically. So if we shift by 8, it's 1, 2, 3, 4, 5, 6, 7, 8. We don't care what this part is. We just care if it's negative, and look, hey, they're all 1s because 8 is all the segments lit up. We are actually passing all, this whole thing to our lights. It's just we don't care exactly what the value is as long as it's negative. And that is doable. The shift left is doable in a single arithmetic combinator, and so by encoding the numbers this way, it's like getting the AND for free, so you only need one combinator. Now you'll see in a moment here that while these are the numbers I use, they come out negative. And what's up with that? So these are the numbers I type into the UI, but this is bigger than a 32-bit int. 32-bit signed int can hold. Now the user interface does display this number briefly while I type it in, but once I close the combinator and reopen it again, you see this number, because when you take this bit pattern, which is, both of these result in this bit pattern, it's just that this is if you assume it's a unsigned 32-bit integer, and this is what happens if you interpret it as a signed 32-bit integer, which is how the game does interpret it. So while I do type in these numbers, these are the numbers that do get displayed in the UI later, except of course the UI does truncate it. It's like 1.2G, and you know. So that's where these numbers came from. You know, this is the program that does the right shift. You can see we're actually doing a left shift to put the number in the right place. Well, the left shift part is right up here, and well, again, it's doing a left shift to get it in the right place, but it's starting at position 32, well, 31, whereas this one down here starts at position 0. Well, yeah, here's the left shift starts at 31, puts the 0 here, puts the 1 in 30, puts the 2 in 29, etc. Whereas the right shift one does it, you know, puts the 0 in the 0, or you know, the 0th bit, the 1 in the first, the first, you know, the second bit, etc., etc. You know, it just depends on if you're counting starting at 0 or 1. Programmers like to count from 0. So that's this program. I'll just briefly say that this is also the program that made the full font. You can see how I actually encoded the letters, and I actually have a similar routine that shifts these to the correct position and figures out, you know, makes up lots of signals, 35 of them per character, and then because we have more than 32 characters, we actually have to make 4 groups of such. But you know, all right, back to me from earlier, explaining how the rest of this works. Okay, here I have all the numbers in. Some of them have shown up as negative. This is negative 1.2G. This is negative 1.102 million. And this one should be negative. This one should be negative. This one should be negative. And this one should be negative. This one should be positive. I'm guessing if I close this and reopen it, yeah, they are now all negative. That's because a 32-bit integer, as these are, can only hold a maximum of about 2.1 billion and change. Anything higher than that, the number gets interpreted as a negative number because of the way numbers are represented in binary. And so we're going to use that to our advantage. But to use it to our advantage, we got to change all of these to be less than 0 instead of greater than 0. So change the first one, copy, paste, paste. 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 Change, copy, paste, paste. Change, copy, paste, paste. So, how do we do this? Instead of having a chess, I'm just going to use a different combinator. Let's move you down so we have room to work. So I'm going to copy this combinator, paste it here just so it has the same numbers, and this will be our input. You know, we'll just call it N for number. So let's try to do this right. We're gonna take our divide and our modulo, and we had A. We'll do A. So we'll take our number. We'll divide it. actually, that's right. It's this end we want connected. That will come in here. We'll take our special numbers and also come in here. So we have our place. The digit in this place should be a 1. Kind of looks a little funny. There's a negative of the next number going over it, but so we want to take each of the numbers and shift it over by the value of this place, and we'll output it on each. And you'll see now we have some positive numbers and we have some negative numbers, and you are 1. So if I hook these up, magically, because of these magic numbers that my program generated for me by me telling it which one should be on, and it shifting the on or offs into the right spot. Oh, there, drag you. So now if I drag this up to a 2, a 3, 4, 5, 6, 7, 8, 9, or down to 0, magically it works, and we've compressed all all of these into one operator, one arithmetic combinator. To do this right, this is fine as a 1's digit. Let's copy you. We'll come over here. Please watch the sound. I will try to stand away. So we don't need this every place. Actually, you don't even need that connection, which I accidentally connected. Here it didn't harm anything, but we don't want to be passing stray signals. If this also had an A, B, C, D, or E on it, that would cause problems. What we do want to do, though, is connect these up. If I set this to be 1, 2, 3, 4, 5, why did that? This should be P, this should be N. Number. That shouldn't be. Debugging. P. Because that's what I wanted. Copy, paste, 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 copy. Alright. You need to be in the one I missed. Paste, 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 paste. Well, they're all 5s. Let's fix that. You need to be divided by 10 to be the tens place. You need it to be divided by 100 to be the hundreds place. You need to be divided by 1,000 to be the thousands place. You need to be divided by 10,000 to be the 10,000s place. We got 1, 2, 3, 4, 5 there, and it works great. Well, not great, because if we just change this to 1, 2, 3, 4, we got a leading 0. So I'm gonna leave the last digit normal because we want a 0 if it really is 0. Let's disconnect that. Alright, we're gonna hook this here and there and to no. Colors. We don't need those mixing. We can do from here to here. That's fine. This is outputting. It would output a P. So if P is greater than 0, we want to output everything. But if it's not, then we don't want to output anything, so that will blank out our zeros. I really hope so. So this should be a 1. Hook that to there and there, and if I copy there to there, we have the 1. So basically this is saying, hey, we have some value here that's bigger than 0, we want to output what we have. If it's 0 or less, well, we don't want to show a 0, so don't output anything. But if it is, well, let's hook the rest of these up this way. And then copy, paste. That works, but to prove it works, we need a number like 30200. So the division here gets 30, and because that's bigger than 0, it was like, we have to display something here because there is a number either here or even higher. That's why the 0 shows up. But when it's only 302, here we're like, oh, the division comes out to be 0, so we're not going to display anything because the number is smaller than our place. And we don't want to display zeros in the leading position. So that's how this 7-segment display works. It's compact. You can put, instead of this here, let's hook this up to here. Let's put a chest here. This outputs an A, the amount. So we want to output A. I'm going to now turn this off, which you see you get 0. I'm now going to change this to be... let's do this. A decider instead. I'm going to say anything. Let's say everything. Everything. So now if I put in here it needs to be A. Sorry. Oh, really? Is that? Let's move you over. You were A with 0. Alright, we'll do this little thing. there. There we go. I don't even need that. Okay. This is a little trick. Before, you know, I said up here okay, we're specifically doing it for pipes. And if I would have put in iron plates, it would not have worked. The way this is set up now, whatever is in here, so I will now put in 50 straight pipes, and it says, hey, we have 55 items in this chest. You know, if I put in 14 more coal, that's 69. 100 tracks, there you go. It's adding everything that's in this box. Now, if you want only specific things, yeah, you can do it like we did before and say, okay, what is that specific thing? You want just straight pipes? Well, there's 51 straight pipes. But yeah, that's the general idea. There will be a blueprint of this linked in the description. I will seven segment SE. I will include there. I'll include one with the smaller segments, 2x2 segments. How did I get from here to here? Really, these are almost the same build. Now, it doesn't look like it at all, but they're very close. Let's get a blueprint, just kind of use it for marking. This whole bottom section here contains the text and what item we want to display. The text is encoded in ASCII. But well, if you can see this one, we want to display coal. These are the ASCII codes for C-O-A-L. This is a capital C. The rest of these are lowercase. And I pass a color. Now, black doesn't really show up on lights, but like this is iron ore. I-R-O-N-O-R-E. Notice 4 is missing. Missing ones are set up to automatically display a space that pass a color. This circuit here is basically a clock. It counts up, and that sends out a signal that lets one of these deciders send its particular thing out on the green line to the display circuit. Now, this, I don't even recall at this point where I got it from, but this is a little circuit that takes the item, like wood or coal, and pulls that value off the logistics network using the RoboPort, and it singles, like the RoboPort outputs all these signals. You can see, well, it's half covered up at the bottom, but it outputs a lot of signals, and somehow this circuit isolates just the one you're passing into it. Technically we're passing all these, but there's no, you know, A, B, C, D coming, you know, or even the colors coming from the logistics network, so it only signals out the value, and that is on this red circuit, and it comes into here. Here is the divide, and you know, we're dividing by 100 million. We're then taking the remainder after we divide by 10, and that gets put into here and here. Notice here's all the shift things. Yeah, so this supports 127 characters. How this works, where we had 7 segments before, here we have an array of 5 by 7 or 35 segments. These only hold 18, so we have 2 of them. That wasn't really a good one to show off. That's a good one to show off. So that's 18, that's 17, and that's all 35. They barely fit in 2, but they do. We have 128 different characters. I said it was a 32-bit int. That means you can hold 32 different combinations of on and off for each of these lights. Because of that, when we have 127 characters, we need 4 sets, because 32 times 4 is 128. We have 127 characters, one of them being space, so there are 128 if you count space. So that's why there's 4 options. So basically we have 4 shifters, and then we do a little math here. We take the number, get the remainder after we divide by 32, and that decides if we take the first, the second, the third, or the fourth set. First, second, third, or fourth set of character representations. These right here, pretty straightforward. It just takes and filters out the color signal onto its own wire, so we can pass that in to color the colored ones without also throwing in, like, the way this works. This is signal 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, all the way up to Y. That's 35. There's 26 letters and 10 numbers, so that gives you 36. We're only using 35 of them. So we don't want the signals that are representing what character we should be displayed to get confused, so we have to filter out each of the colors independently with these deciders, saying, hey, if this color is greater than 0, pass it on to this green wire, and then this green wire is independently sent over here. So this is, one signal is 1 pixel. This is double size, so you can see the pixels are 2 by 2, but otherwise this circuit here is identical to this circuit here, and we just have a little extra circuit that handles first getting the digit that we want, and then the numbers happen to start at 48 in ASCII, so we add 48 onto that. So 0 is character 48, 1 is character 49, 2 is character 50, etc. So that's why we got this little thing here. And it's basically the same thing, just a lot more complex, because I had to write the program to figure out all these numbers. If I want to change how one character looks, and there actually is a character I'd like to change slightly, I have to refigure out all the, basically changing one character is going to change all the numbers in one of these 4 sets. So yeah, yeah. There's one character that didn't come out quite like I'd like to, but if I didn't tell you about it, exactly which one it was, you probably wouldn't notice. I guess this has gone on quite a lot longer than I thought it would be. I did mention rocket launches before. So, yeah, we got every item. There's 210 items by my counting. These are rows of 64. Again, that's a base, it's a computer number if you want to call it that. So this is 193. Actually, I do start at 1 and not 0, although I do have a 0. Anyway, so we come over here and we get to rocket silo, which is the last thing on the list. And then I have a few special ones. This is the number X term run over, which we weren't. But you can manually change this one. This is the numbers of rocket launched, and while I do have it set to n equal to 1, I have a little mechanism here. This inserter is set to read hand and pulse. And then this takes satellites, which is what this is. Assume that there's a rocket silo here, and this is the arm that loads the satellite in. This takes satellites, adds nothing to it, and outputs it as satellites, but its input is hooked to its output. So this works like a memory cell. As you can see, we have moved 3 satellites into the storage chest, or into the silo. It's a chest in this case, and this is remembering 3. So if we just take one out, hey, look, this is still remembering 3. This is not hooked up to the chest; it's only hooked to the arm. So if I put the satellite in here, the arm will pick it up and send it another pulse, and that makes this count go up to 4. This is then just converting the satellite number to n, because that is, if you don't have an actual item like we have over here, you need to pass n as the value you want to display by this display. So now, well, we just miss it. When this gets back around to satellites, which will to rockets launched, not satellites, it will display 4. Well, technically it will display 5 because I'm adding 1. Just because if there's nothing in here, it flashes past it, and I just wanted that message to show by default. Power. If you hook a wire up to an accumulator, it will output A as the percentage. This is stuck at 67% because the way I'm powering this with these passive energy sources, they never go up or go down from, they never take any from accumulators, but they never give them to it either. There's an active energy source that will give power. That's how I got this powered up more than halfway. So this is then converting A to N. I could have just put out N from here directly, but whatever. And that is how we get the power level on here. Oh, and this is the time. Again, I have a counter here, basically. It's a memory cell, but it always gets 1 added to it, since that happens once a frame. This is the count, basically 3.3 million frames since this was been placed. And then we just divide by 60 to get seconds, because this game should be running at a frame rate of 60. And that's how I did the time. So there's room here for you to add your own messages. You just have to look up an ASCII code table and put them in. If I didn't explain it correctly before, this is the first character, the second character, third character. 3 would be the fourth. And then if you know hexadecimal, after 9 comes A, B, C, D, E, and F. There are 16 character displays at the top. And that's how this works. It's kind of just like this, but more complex. We have 35 segments, if you want to call them that, instead of 7. So, that's how these displays work. You can hook them up to fluid tanks, especially this 5-digit one. You can hook them up to chests. You can go crazy and hook them up to your logistics network and cycle through all the items and display them. Thanks for watching. I hope you enjoyed this. If you have any questions, leave them below. And I'll see you guys next time. Hopefully finishing off my all-item train run. I'll see you then. Thanks for watching.